Hey, it's Dr. J. I'm back for part 2 of the section 5.3, graphing polynomials. Already have an example ready to go here. So in the last section, the last portion of the section, we were kind of starting with the equations and then developing a graph or developing some theory about the characteristics of the graph. In this section, I'm kind of going to turn it around the other way for most of these problems. I'm going to give you a graph, or perhaps I'll give you a verbal description or a written description of the graph, and then you will then give me the equation. So it's kind of like the other side of the coin here. So go ahead and write an equation for the polynomial shown in this graph here. So the first thing we want to do is we want to look at the zeros, or the x-intercepts. Also known as the zeros. Okay, and that will give us the factors. All right. So we have a 0 at -2. So we have a factor of x plus 2. Remember, the solution, or the 0, always has an opposite sign of the factor. And then now look at the shape. If the shape looks like a parabola, then you're going to make the multiplicity 2. All right, if it's the shape of a parabola, it's multiplicity 2. If it's the shape of a cubic, then it's multiplicity 3. And if it's the shape of a straight line, it's multiplicity 1. And there are other multiplicities in the real world or in advanced calculus. In this class, I'm basically limiting it to 1, 2, or 3, all right? Because that's the basic idea here. Ignore the y-axis for now. So first, just look at the x-intercepts. We'll get to this later. All right, so here we go. We have x equals 1. So our factor will be x minus 1. And then look at the shape. The shape looks like a cubic. So that will be third power. Finally, you've got a 0 at 4. X equals 4. So your factor is x minus 4. And the power is 1 because this looks like a straight line. And 1 is a special power. Of course, you don't have to write it. So you can just leave it blank like that. Okay? Or you can write it. It doesn't matter. I'll mark it right either way. OK, so we're going to then write an equation. Y equals x plus 2 squared, x minus 1 cubed, and x minus 4. And then we don't know what the leading coefficient is. The leading coefficient is unknown. Call that the leader. So that's when we're going to use the y-intercept to find A. All right. So you use the y-intercept last, all right, to find the value of A. I'm going to need to use some of this space up here. OK, so what do we have? We have y equals A times x plus 2 squared times x minus 1 cubed times x minus 4. And we know the y-intercept (0, 2). So 0 would be x and 2 would be y. So I'm plugging in all of these x's, 0 for all the x's, and then I'm plugging in 2 for the y value. I don't really need the graph anymore. I can just kind of put this aside over here. Okay, and this should be relatively easy to solve as long as you've set it up correctly. I know I've mentioned this before. At this point in the semester, I've already taught you all the techniques for solving. At this point, you're just using what you already know, or maybe refining it, getting better at it as you go along, and perfecting the art. So you got 2 squared, which is 4. You got -1 cubed, which is -1, and then -4. So multiply all these together. You're going to get +16. You could write it this way. I don't really care. I mean, if you say A times 16, that means the same thing as 16 times A. And then divide by 16. And then there's your A. 2/16 is the same as 1/8. And then so come over here and replace A with whatever the value is. You can use a decimal or a fraction. I prefer fractions, but you could also do 0.125 as a decimal. You know, the only exception to that is the ones that I've mentioned before. If it's an irrational number or a repeating decimal or something like that, then you definitely want to leave it as a fraction. Well, if it was irrational, you couldn't write it as a fraction anyway. So, and then you can either write it as y equals, or sometimes the problems will say f of x equals. Just follow the directions, whatever the problem is insisting that you do. Most of these problems are set up so that the left-hand side is simply the name, and all your work is on the right-hand side anyway. So if you accidentally mistype it or something, that's something that's easily fixable if you catch it. And if you don't catch it, let me know, and I'll take a look at it. Okay. So there you go. This is the function that produces this graph here. I'm not asking for the end behavior, but you could very easily mentally check, just mentally check, especially on the final. You might want to check your own answers. If both arrows point up, that means the degrees should be even, okay? And the leading coefficient should be positive, right? So far so good. The leading coefficient is positive, and the degree is 1, 2, 3, 4, 5. And remember, there's an invisible 1 here, so the degree is 6. So you could check the end behavior. Look at the end behavior to check. It should be 1/8 x to the 6th. Check. 1/8 and then x to the 6th. No, that's not the entire answer. That's just what the end behavior would be, 1/8 x to the 6th. And it does seem reasonable that the arrows go in the right direction. Okay. If you had one of these factors incorrect, you might notice that before you submit your answer. Or not. I hope you do. You never know. Want to try another one? Let's try one more. One more of these. Same question. Notice the graphing board is really not necessary. For these types of problems, I could just as easily do it on the whiteboard. I do like the fact, I don't like the fact that well, maybe while I'm waiting for this to refocus, I will draw the graph. Hopefully by the time I'm done drawing the to make my graph a little less messy, I'll just assume that each one of these tick marks represents 1 unit. All right, I'll give you another second to come back down. Come back to me. There we go. All right, so find the polynomial function shown in the graph. Same type of question. Okay, same type of question. Assume that each unit is 1. Each tick mark is 1 unit, so that'll be -2. That'll be 3. And this looks like -3. All right. Look at the x-intercepts, or the zeros first, and then do this last. So this is going to be last. If you try to put that in there now, it'll typically screw everything all up. All right. So wait till the very end. All right, so we got y equals. So this will be x plus 2. Opposite of -2 is +2, and it looks like a parabola, so it's squared. Doesn't look like we have any straight line behaviors here. They're all curves, so this is a cubic. X minus 3 cubed. Okay. And then finally, we'll put the a in the front. That's our leader. And then we'll use 0, -3 for x and y. So we're going to get -3 equals a, 0 plus 2 squared, and 0 minus 3 cubed. So that'll be 4 and -27. That'll be a negative, what's that, 100 and something, 108? I just guessed. You might want to do that carefully. 4 times 20 is 80. 4 times 7 is 28. So 80 and 28 is 108. In this case, I'm not going to rewrite it. I'm just going to go ahead and divide by 108. Negative 108. Negative divided by a negative is a positive. 3 goes into 108. How many times does 3 go into 108? 36 times. I almost blew it. My brain was telling me 36, and I almost wrote 36 as the answer. Because the numerator is, of course, smaller than the denominator, it is 1/36. There's your A. So there you go. Once you've done that, then just give me the answer. You could say y equals, or you could say f of x equals, or sometimes we say p of x equals, polynomial, whatever the question is indicating. So you've got 1/36, and then times all these factors. X plus 2 squared, x minus 3 cubed. The order does not matter. You can type your answer in any order you like. Okay, so that's sufficient for the graphing problems. We're still going to do more graphing, but now I'm going to describe the graphs, using words instead of with a picture. Same idea, just sound instead of light. You can hear what the graph sounds like. Find a degree 3 polynomial having zeros at -5, 2, and 7 with a leading coefficient that's that A, also known as the leader, of 1. The first thing I want to mention, these types of verbal problems are always going to tell you the degree. Wait on that. Use it to check your answer only. Okay? Because you might be tempted to go like this. Right? You're going to read the problem. It's going to say degree 3, and you might be tempted to just write x to the 3rd, and then try to, continue solving the problem from there. If you do that, it's almost like you've lost right before you even begun the game. You've already lost. So you have to just read it and then know, wait a minute, I'm not going to let that degree 3, cause me to screw this whole problem up. Just continue solving the problem, and then when you get done, go back and make sure that your answer is degree 3. Okay, so we want a polynomial whose leading coefficient is 1. Right? I usually do that first. Leading coefficient. Zeros are the opposite of the factors. So -5 becomes +5. 2 becomes -2. And 7 becomes -7. All right. If no multiplicities are given, so it doesn't say anything about multiplicities, then all factors occur once, which means they have a power of 1. Right? If you want to put the 1s here, you can, but I typically don't. Yeah. If you want to, you can, but I mean, typically if something is 1, we just don't write it. All right, so there you go. That's your answer. There you go. It's essentially a free answer. If you get this problem on a test, you should be like, thank you, right? Like, all you have to do is read the question and write down the answer. Requires very little mathematical skill or calculation or anything like that. It's mostly reading comprehension, which is about 90% of what this class is about. Okay. Now let's try one that's not free. All right, you know how I work, right? I give you a free one, and then I'm going to make you work for everything else. How about this one? Find a polynomial. I'm just going to abbreviate poly of degree 6. Having a leading coefficient of 1. Coef for coefficient. A 0 of multiplicity. Zeros of multiplicity, so plural, of multiplicity, it looks like multiplicity. Multiplicity 3 at x equals 4 and 2. And a 0. Am I saying this right? Slow down, Dr. J. Find a polynomial of degree 6 having a leading coefficient of 1, a 0 of multiplicity 3 at 4. I'm reading it incorrectly. And, there's the and, multiplicity 2 at 0. And another and, multiplicity 1 at -3. Now we're talking. Make sure you have the problem written down precisely or read it carefully before we dive too far into it. I almost screwed this one up just by reading it too quickly. Okay. All right, here we go. So polynomial, p of x, leading coefficient of 1. Okay, put a 1 in front. Or not. Right? You could just leave it. If it's not there, it's a 1. Let's see, multiplicity 3. Multiplicity 3, so that's the power, 3, at 4. So that would be x minus 4. Yeah. So remember, the multiplicity is the same as the degree or the power of the term. Multiplicity 2 at 0. So there's multiple. Here, I'll use the color coding here. I don't know if that makes it any easier to follow. So multiplicity 2, that's the power of 2. And then 0 is the factor, x minus 0. And then multiplicity 1 at -3. So remember, when your 0 is a negative, your factor is a positive, multiplicity 1. This is your answer. You know, if you're doing your homework and you just want to move on to the next problem, you could certainly type it in this way. I like to simplify. A little bit. Just a little bit. I don't want to do too much work. The first thing I do is I get rid of all my 1s. There's no need to write the 1s. And then I also get rid of a 0. What's the point in having a 0 there, right? X minus 0, we might as well just write that as x. Okay. And then because this x looks a little bit squished, yeah, it's like, it kind of feels like boxed in there between these guys, typically we move them out to the front. This is the way the problem would look in a textbook, or if you were, presented with this problem, from scratch. This is the way it would typically be written. All right. So this is my answer. I'm not that picky. If you leave it unsimplified, if you leave all the 1s in place and you have it in just some scrambled order, that's okay. It's fine. At this point, I just want you to be able to read the question, get the right answer, and then I'll leave it to you to decide how much you want to dress up your answer to make it look pretty. Okay. Let's try another one. A lot of these today, so not too much variety today. Just trying to cover everything, cover all our bases. Find a polynomial of degree 4 Oh, you know what? I didn't mention this before I get too deep into this problem. What did I say about the degree? You should use it to check, right? I know I didn't do that on my last example, but just really quickly before I erase this beautiful answer here. Look at the degree All right. It's 2 plus 3 plus 1, which is 6. Check. So in the last example, the one I just erased, or I was just about to finish erasing, I said, use the degree to check your answer, and then I got excited and forgot to check. But look here. The degree should be whatever it says it is. Yeah, 2, 3, 1. The degree better be 6. This time I'll remember to check that before I get too far down the road. All right, so we want a degree 4 polynomial with a 0 of multiplicity 2 at 1 and zeros of multiplicity 1, so plural, zeros of multiplicity 1 at 2 and negative 4. It has a y-intercept at 0, negative 8. Okay, so let's just kind of dissect this a little bit. We're going to use the degree to check. All right, so don't do it right now. All right, you might be tempted to say x to the 4th. Don't do that. I'll screw everything all up. All right. Also, we don't have the leading coefficient. No leading coefficient was given. So we're going to use this to find A. Just like we did in this problem where we drew the graph and we used the y-intercept. Actually, it's upside down. We used the y-intercept to find what A is. Well, I'm doing the same thing here. Instead of drawing the picture, I'm giving you a verbal description of the y-intercept, and you can use that y-intercept to find A. All right. Let's start building our polynomial. All right. So we've got, what do we got? 0 of multiplicity 2. Multiplicity 2 at 1. So that's x minus 1. Okay, and then zeros of multiplicity 1, which really means you don't have to worry about the power, at 2 and negative 4. So x minus 2, x plus 4, and these will both have power 1 if you like. Or just don't put a power at all. All right. We put A right here in the front. I like to call my P of x y while I'm solving it. I know I've mentioned that in the past. You can leave it as P of x, but it's just so much easier to just write the letter y. It also, causes less confusion where you might accidentally put these in the wrong place. So 0 is x, and negative 8 is y. So make sure you put it in the right spot. Negative 8 goes here, and 0 goes where the x is. And again, this might look complicated, but it's just a basic one letter, one variable linear equation. Should be very easy to solve. So I've got negative 1 squared. That's just 1. And why don't I just kill two birds with one stone? This is going to be a negative times a positive, which is a negative 8. So this is negative 8 equals negative 8a. I like to write it that way. And this really annoys me when I do all that work and I get 1 for A. I'm like, really? I had to do all that to get an answer of 1? But yeah, it won't always be 1. Sometimes it'll be 2. Sometimes it'll be -1. Sometimes it'll be -2 or -0.5, or you never know what's going to happen. But then when you get 1, it's kind of like, wah, wah, I got 1. Thanks. Okay, and then come back to here. You got your A. Your A is 1. So you can just put it, or you can not put it. It's up to you. And I do like to go back and call my function p of x, or sometimes I call it f of x, whatever you like, or whatever it's called in the problem. Yeah? It's not whatever you like, I guess. It's whatever I ask you to call it. When you start having your own functions, you can name them whatever you want. You'll be the boss at that point. You'll be the parent. You'll be the mother function. All right. Let's try another one of these. I mean, might as well. So this is what we're doing today, right? So example 6. Oh, did I check my answer? I'm really bad at checking. Look. Degree check. Add up all the powers. 2 plus 1 plus 1 equals 4. Check. Make sure that it's the right degree. The degree is, in fact, 4. How about this one? Find a polynomial of degree 3 with a 0 of multiplicity 2 at x equals -1. And a 0 of multiplicity 1 at x equals +1, and a constant term of -5. Or maybe I'll say it this way. The constant term is -5. Tomato, tomato. All right, so p of x, polynomial, multiplicity 2 at -1, multiplicity 1 at +1. Okay, and the constant term is -5. We haven't talked much about this, but the constant term is the same as the y-intercept. Yeah. Now, I mean, you could say, really? You just told me that for the first time. But if you think about it, when you have a polynomial, you know, p of x is, you know, x cubed plus blah, 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 blah. You know, let me just make something up. X cubed plus 2x squared minus 4x minus 5. What that means, the constant term is the last term. That means that if you plug 0 in for all the x's, all these zeros cancel out, and you just get -5. And so that's the same as the point 0, -5. Yeah, that's the y-intercept. So those are synonyms. Y-intercept, constant term. They basically mean the same thing. Yeah. It's kind of like saying x-intercepts and zeros. Well, those mean the same thing as well. Yeah. So what are we going to do? We're going to call this y. I should have just done that to begin with. We're going to put our a in front. And we're going to solve. All of our x's are going to be 0. Yeah, all our x's are going to be 0. And our y is going to be -5. 1 squared is just 1. What's that? 0 times -1 is just -1. So this is -1 times a, I guess. Or you could just say -a. Yeah, negative times a positive is a negative. And then you're going to divide both sides by -1, and that's going to say that my a is 5. So come all the way back over here and put 5 in front as the leader. Coincidence that it came out to be 5. I think that's because these were both 1s. Had these numbers been something other than 1, then this probably would not have stayed 5, all right? So there's your answer right there. Really quickly, mental check before I forget. At the very end, look at your degree. You have degree 2. You have degree 1. You're going to add those together. Check. It is the right degree. It's degree 3. All right. If the degree is not right, the answer is definitely not right. Just having the degree right is not a guarantee, but it's certainly a good indicator that it's probably right. So I'd rather have some confirmation than, an absolute, negation of the truth. I don't want it to be total nonsense. All right, I know these kind of get exhausting. The last example of something like this would be where I don't give you the leading coefficient, I don't give you the y-intercept, and I don't give you the constant term. Sometimes referred to as the worst case scenario. So find a poly of degree 4 having a 0 of multiplicity. I'm getting tired of writing multiplicity. I'm going to write mult 2 at 2 at x equals 2. And zeros of multiplicity 1 at 0 and -1. The graph passes through the point 5 and 162. All right. So again, remember, degree 4, wait. Look at the multiplicity and the zeros. Multiplicity and the zeros. Look at those first. So I've got x minus 2 squared, x minus 0 to the first, and x plus 1 to the first. And then an a here. And now the point is 5 is x and 162 is y. So put them into here. 162 A couple things that you can get rid of if you like. You can get rid of the powers of 1, and you can get rid of the minus 0. That's about it. So I don't need the first power. Obviously, if a number doesn't have a power, it's 1. And then I don't need to say 5 minus nothing. I can just say 5. Yep. All right, let's see what this comes out to be. 162. Oh, God, is it going to come out to be 1? Let's see. I sure hope not. 9 times 30. Oh, good. That's going to be 270. Yeah, 3 squared is 9. 5 times 6 is 30. 9 times 30 is 270. Divide by 270. Simplify this if possible. Let's see. 162 is 81 times 2. 270 is 135 times 2. So I cross off the 2's. Can I do any more? Let's see. 81. 81 is 27 times 3. That's 81. 135 is, what's that times 3? Something times 3. Got it? Is it 35? No, 45? 45? 45 times 3. Yeah. 45 times 3 is 135. Cross off the 3's. Can we go more? Let's keep going. Don't stop. 27 is 9 times 3, and 45 is 9 times 5. So the final answer is 3/5. Or for A. That's A. Yeah. If you really get impatient, you can just use a calculator, and you could have jumped right to here. That would be 0.6. I don't care. Either way, you could say 0.6 or you could say 3/5, and it's the same thing. All right, so then I come back to my answer here, and I write it P of x, polynomial of x, or sometimes we call it f of x, or sometimes we just keep it as, y. And then you put your 0.6 in front, or 3/5, same things, same thing. And then x minus 2 squared, x minus 0, and x plus 1. And then if you really want to be neat, you can get rid of the minus 0, and you can write it like this. X minus 0 is the same as just x, so you can move it to the front. That's, of course, optional. So this would be my answer. That's the one that I like. And I'm not a huge fan of decimals over the last, 6 weeks or 8 weeks or however long it's been. By the time you watch this video, you might have noticed I rarely ever use decimals. But when decimals come out exact and they don't repeat and they don't do all kinds of weird things, I don't mind a decimal. And once in a while, it's not a bad idea. So I don't know. I still prefer fractions, but if I can take it, I'll get it. Or if I can get it, I'll take it. All right, that's about it for these types of questions. We're going to go back to some graphing questions, and we're going to talk a little bit about what happens with graphs when you can't factor them. Oh, not graphs. Sorry. Sometimes polynomials are difficult to factor. So the graph is not easy. I mean, if there's anything that you've learned in the last however long it's been since you started this course, if there's anything you've learned in our time together, or your time listening to me, it's that if I give you something that's already factored, I hope you all realize I'm essentially giving you the answer. I'm basically cooking it up in advance and saying, here, take it. It's all ready for you. All you got to do is do it. Yeah? But sometimes you get a polynomial, like in example 8. Something like this. Yeah. So factoring this is not easy. It's not impossible, but it's not easy. All right. You could certainly try. You could try guessing. Yeah. You can't use the quadratic formula, yeah, because it's not quadratic, it's cubic. There is a thing called the cubic formula, but it is so long and tedious. You would be better off just guessing. Yeah. We're going to do neither. We're going to do neither. Okay. What we're going to do is we are going to use the y-intercept. Yeah. Just because guessing takes too long. All right. Now later on in chapter 5, if we have time when we get there, if we don't have time, we might never see it. But later in chapter 5, there are techniques which make the guessing process a little bit faster. So you're not just randomly guessing numbers. There are some ways of sort of educated guessing so that you're guessing things that are actually reasonable, but still ultimately you're just guessing. All right. So the first thing we're going to do is we are going to use the y-intercept. The y-intercept is always very easy. Just plug in 0 for x. Yeah. Plug in 0 for x, and you're going to get 3. So you get 0, 3. Yeah. 0 is your input. That's your x. 3 is the output. That's your y. So your intercept is 0, 3. Okay? That's always going to be easy. The x-intercepts are not easy unless the polynomial is already factored. And I've given you plenty of problems where it's already factored. So this is one example where it's not already factored. So we need a theorem. It's called the intermediate value theorem. Okay. I don't want to lose this, so let me just write it over here. Here, I'll just write it up here. X cubed plus 2x squared plus 3 save. Okay, we'll come back to that later. And we'll also save this also. All right, so I hope you all are still familiar with the concept of graphing. We have the y-intercept, very simple, but the x-intercepts are not always simple. You might want to, have some way of finding them. So the intermediate value theorem is a theorem that says if f is a continuous function, and f of A and f of B have opposite signs, then there exists a C between A and B such that f of C is exactly equal to 0. Now, I'm actually going to call this intermediate value theorem version 2 because there actually is an original version of the intermediate value theorem, which it's interesting that in pre-calculus or in college level algebra, we often don't talk about version 1. Version 1 says that every value between f of A and f of B exists. That version of it's not very useful for us right now, so I'm just going to pretend like that version of the theorem doesn't exist. As a corollary to the original intermediate value theorem, which I just am calling version 2. In this class, it's the only version, so you don't have to worry about there being a version 1. Okay? So, having said that, I really didn't need to mention that, but if you're a purist out there and you Google the intermediate value theorem, you might find that there is another theorem that I'm not talking about in this particular case. I'm talking about the special case of C. Okay? It's also a little confusing, all these different A's here. Sometimes we get confused with which A we're talking about. These A's are just the English word A, the first word in the dictionary, A. These A's are actually numbers A. So sometimes we do things like this. We make our A's look different. So you can tell, what A are you talking about? Well, this is my math version of the letter A, which some people think looks like the letter D. So I don't know if I'm making it worse or better, but whatever the case may be, A and B are numbers. Okay. I sometimes think that makes it look worse, so I'm just going to go back to the old-fashioned A, traditional value A. Okay, so this is the intermediate value theorem. Let me kind of give you the idea before I actually use this problem here. So you have your x-axis, you have your f of A and your f of B. They have opposite signs. All right. Now it doesn't matter which one. Sorry, let me put it in this way. All right. We assume A is less than B. So A is the one on the left and B is the one on the right. So they have opposite signs, which means one of them is positive and the other one is negative. It could be the other way around. It could be that the f of A is the positive one and the f of B is the negative one. We don't know. All right. And so we have some polynomial. All right. I've tried to make it look like a polynomial. So it's got a shape of a polynomial. Right. This is the point C. Okay. And so f of C is equal to 0. So this is C, this is B, and this is A. And notice that C is between A and B. And I know that it must be somewhere in between. And why is it equal to 0? Because it's exactly on the x-axis, and that's what it means to be equal to 0. It means that you are on the x-axis. That's why we call it a 0 or an x-intercept. Okay, you're probably thinking, hurry up, get on with this problem, right? This is taking forever, right? But you're going to need this theorem, right? It's going to have several iterations of this theorem. All right. So let's see. Let's see what happens, right? Let's use this polynomial here. I know my polynomial was called P, but I'm going to go ahead and give it a name change. We're going to call it F. Polynomials are whatever you want to call them. All right. So what do I know? I know, let's say, what's f of 1? Actually, I already know f of 0. Yeah. F of 0 is 3. Yeah. What's f of negative 1? F of negative 1 is negative 1 cubed plus 2 times negative 1 squared plus 3, which is equal to negative 1 plus 2. Notice this is a negative squared, so it's going to stay a positive. And then plus 3. All right, what's that going to be? That's going to be negative 1 plus 2. That'll be 4. Do these have opposite signs? No. So keep looking. Try negative 2. Now, when I say keep looking, you don't have to look very hard, all right? It's typically the same numbers we used in our graphing. It's either going to be 0, 1, 2, maybe negative 1, maybe negative 2. If you don't find it in those places, then you might have to widen your search area, but you're not going to have to look very hard to find these things, okay? They'll be right in the last place you look. Okay, so negative 2 cubed is negative 8. Negative 2 squared. Negative 2 squared is 4. 4 times 2 is another 8. And then plus 3. We still don't have opposite signs. Means I'm going to have to look a little harder. Let's try negative 3. Negative 3. Negative 3 cubed plus 2 times negative 3 squared plus 3. That's negative 27 plus negative 3 squared is 9. 9 times 2 is 18 plus 3. Here we go. We got it. Negative 27 plus 18 is negative 9. Negative 9 plus 3 is negative 6. Yay, we found it. So we want opposite signs. So look what just happened. Here's my x, here's my y. I've got 0 and 3. Yeah, 0, 3. Okay, I've got, I'm just going to skip this one. Let's go to this one. Negative 2 and 3. Yeah, I take that back. I don't want to skip that one. I think it adds a nice touch to it. I've got negative 2 and 3 right there. And then look what happens. By the time you get to negative 3, this graph is all the way down here at negative 6. 4, 5, 6. All right, that's negative 3, negative 6. And so this graph looks like that. Yeah. And it's a cubic. Right. And I know that somewhere in between, this is my value C. C is between negative 3 and negative 2. The theorem doesn't tell you what C is, it just tells you where it is. I know it's somewhere between negative 3 and negative 2, but I don't know anything other than that. Okay. How do I know this turns around and goes up and doesn't just continue going back down? If it continued going back down, this would be a parabola. It would be a square function, and it's not a square function. So I have to follow the shape of a cubic. I guess if you really want to, beat this up a little bit more, you could keep trying to find another c. There could be other values where it touches the x-axis, but in this particular example, that doesn't happen, so I'm not going to waste your time. I'm just going to tell you that this is the graph. All right. So this is the graph of the function. We know the y-intercept. We don't precisely know the x-intercept, but we know somewhere in between -3 and -2, it must have an x-intercept. That's the best you can do with a graph that's not factorable, or at least a graph like this that might be very difficult to factor. For the remainder of the questions, I'm just going to solve them, and I'm not going to actually draw the graph. Although I might do a rough sketch just to kind of give you the idea. But the last couple examples are just using the theorem. It's called the IVT, the intermediate value theorem. So let's say f of x equals x to the 5th minus 2x cubed plus x minus 1. And see, does it have a 0 between x equals 1 and x equals 2? All right, so let's figure out what f of 1 is. F of 1 would be 1 to the 5th minus 2 times 1 to the 3rd plus 1 minus 1. It'd be 1 minus 2 plus 1 minus 1. I guess I probably could have done that in my head. 1 minus 2 is -1, plus 1 is 0, minus 1 is -1. If you're good at mental math, you can just jump right to the final value. As long as it's correct, it's OK. Let's do f of 2, 2 to the 5th minus 2 times 2 cubed plus 2 minus 1. I don't know if I can do that with all in my head. So 2 to the 5th is 32, right? 2 times 2 times 2 times 2 times 2. 2 to the 3rd is 8. And then times another 2 would be 16. Plus 2 minus 1. So that's 32 minus 16, which is 16. Plus 2 is 18. 18 minus 1 is 17. So since f of 1 and f of 2 have opposite signs, see, look, one of them's negative, the other one's positive. There is a c between 1 and 2. Right. Or if you like, you can be very precise. X equals 1 and 2. Right. Such that, so yes, the answer is yes, such that f of c is equal to 0. Again, we don't know what c is. We just know that it lives somewhere between 1 and 2. Here's our c, somewhere between 1 and 2, and the graph must pass through that point. right? When you're at 2, you're way up here at 17. That's above. And at 1, you're down here at -1. You're below. And so this is a continuous function. The word continuous just means unbroken, smooth, continuous function. And so there's the C. All right, somewhere between 1 and 2. If you take more advanced math, perhaps pre-calculus, trigonometry, hopefully calculus someday, you might actually find exactly what C is. All right? But not in this section. It's not going to happen. All right. I think one more ought to do it, huh? Example 10. Use the IVT to determine, I should have just said same question. If f of x equals 2x to the 4th plus 5x to the 3rd plus x squared has a 0 between, I don't know, x equals -3 and x equals -2. I don't know. Yes or no? Let's see. Now, I should make sure that I clearly I want to make sure that I clearly state what the IVT is doing. It's guaranteeing that there's a 0. So the IVT is like a guarantee that you will find it. It doesn't tell you what it is, right? It's just saying you're guaranteed to find it, but I'm not telling you where it is. But it's guaranteed to be there, okay? So let's go ahead and see what this one comes out to be. -3 to the 4th plus 5 times -3 to the 3rd plus -3 squared. That'll be 2 times 81, -3 to the 4th, plus 5 times -27, -3 cubed. Okay, plus 9. So that comes out to be 162 minus, what's that going to be, 135? You might want to double check me. 5 times 20 is 100. 5 times 7 is 35. Plus 9. Oh, my brain is tired. 162 minus 135. I don't know where my calculator is. I don't know. What is that? 5, 17, and then plus 9 is 26. I sure hope I got that right. If you don't want to gamble and your brain is tired, use your calculator. 162 minus 135. Oh, 27. 27. I'm glad I used my calculator. Plus 9 is 36. I don't need the calculator for plus 9. Let's see. -2. So 2 times -2 to the 4th plus 5 times -2 to the 3rd plus -2 squared. So 2 times 16 plus 5 times -8 plus 4, 32 minus 40 plus 4, -8 plus 4, -4. Check, check, yes. Yeah, again, they have opposite signs. So if they have opposite signs, the answer is yes. I was really hoping to give you one where the answer was no. But I just have a list of examples, and it turned out that they both came out to be yes. So the problems themselves will vary. The answers could all be yeses. The answers could all be no's, or they could probably more likely have a variation. Some of them will be yes, and some of them will be no. That'll do it for me. We're done with section 5.3. Until we meet again next time, this is Dr. Jordan signing out.